In the last video, we defined what it means for a set of vectors to be linearly dependent and linearly independent. As a reminder, we say that a set of vectors is linearly dependent if one of the vectors is a linear combination of the others. Otherwise, we would say that that set of vectors is linearly independent. And in this video, we're going to look at several examples of specific sets of vectors and show how to determine if they are linearly dependent or independent. So to start with, let's consider these three vectors, v1, v2, and v3. These are vectors in R4. And the question is, or the goal here is to determine if these vectors are linearly independent. So we would like to know if we can write one of these vectors as a linear combination of the others. And so one way we can approach this is by setting up a matrix where these vectors are the columns of that matrix. So we'll just do that here. Okay, so we end up with a 4x3 matrix in this case. And then we will row reduce this matrix. And so I'm going to just show the result of that. You can either use one of our technological tools to check this yourself, or practice our row reduction algorithm if you'd like. And so this reduces to the matrix 1, 2, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. And from this, what we can actually see is that if we kind of ignore that third column and just focus on our first two, that actually our second column is exactly twice our first column. And so if we go back to our original vectors, we can actually see that v1 and v2 are precisely scalar multiples of each other. In other words, v2 is equal to 2 times v1. And so since we can write v2 as a linear combination of the other vectors, so the way we would do that here is actually that v2 we could write is equal to 2v1 plus just 0 times v3. And so v2 is a linear combination of v1 and v3. And so this set of vectors, this set v1, v2, v3, we would say is linearly dependent. And one thing I want to point out is that the final row reduced matrix here tells us where our pivots are. And we have 2 pivots in this particular matrix. And so one thing we're going to see later is that we can tell whether or not a set of vectors is linearly independent if the matrix consisting of those vectors as its columns has fewer pivots than the number of columns. So that's what we see here. And we'll point that out later, but we'll do a few more examples first. All right, let's try this one. Again, 3 vectors, this time, new vectors here and still vectors in R4. So let's once again sort of put those vectors in a matrix. So they become the columns of a matrix. And can row reduce this. Again, if you want to practice that algorithm by hand or practice using one of our technological tools, then you can go ahead and try that. But here we will row reduce this, and we get this particular matrix. And so, what we can see from this is that actually we would not be able to write any of the vectors as a linear combination of the other vectors. And we'll talk a bit more later on about, sort of how we can tell this. But one thing we can notice is that we do end up with a pivot in each column. And so that's sort of the quickest way to tell. But the why does a pivot in each column tell us that these are linearly dependent, is something we'll be exploring a little bit later on. But in any case, this set of vectors, v1, v2, v3, is linearly independent. Okay. Let's go to the next example. this time 4 vectors in R4. Again, we'll set up this matrix. And we can row reduce this. This would end up being the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And again, pivots in each column, so these vectors are linearly independent. Next example. Okay, again, let's set up our matrix. And this one can row reduce to reduce our echelon form, and it will look like this: 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, and then all zeros. And so from this, we can see that there is not a pivot in that last column. And so these are going to be linearly independent, or excuse me, linearly dependent. One kind of quick way to see that is that we can sort of pretend that we weren't just kind of row reducing a matrix at random. We were row reducing the augmented matrix for a system that had, was looking for solutions to the equation ax equals b, where b was that fourth vector, v4. So by, kind of adding that vertical line in to the matrix, we've kind of, changed, at least on the surface, what appears to be what we were doing here. And so, when we reduce that, we can actually see that this does have a solution. And in particular, that solution essentially says, so if, x consists of, maybe we'll call it actually x1, let's do it like that, x1, x2, and x3, then what this tells us is that x1 would equal 1, x2 would equal 1, and x3 would equal 1. And so our solution to this is just 1, 1, 1, meaning that v1, 1 times v1 plus 1 times v2 plus 1 times v3, I guess, equals v4. And we can, test this. Let's just go back up and check. And so, kind of just adding across 1 plus 0 plus 2, that is 3. 0 plus 1 plus 1, that is 2. 2 minus 1 is 1, plus 0, that's 1. And then 1 plus 2 plus 1 is 4. So that is, in fact, true. And since we can write one of these vectors as a linear combination of the others, this set is linearly dependent. So hopefully this gives you a little bit of insight into why a pivot in each column versus not having a pivot in each column can tell us whether or not these vectors are linearly dependent as a set. Let's look at one more example. We've got now 5 vectors in R4. We'll set up that matrix again. And look at the reduced row echelon form of this matrix. It's now a 4 by 5 matrix, and this reduces to this 0, 1, 0, 0, 2, 0, 0, 1, 0, 1, and 0, 0, 0, 1, 2. And we only have 4 pivots. And so we have a column without a pivot. And once again, what I'll do is kind of draw a vertical line down here to represent the fact that, we're not just row reducing a matrix, we're row reducing the augmented matrix for a specific equation. And this equation says that x1 equals 0, x2 equals 2, x3 equals 1, x4 equals 2. So this basically tells us that 0 times v1 plus 2 times v2 plus 1 times v3 plus 2 times v4 should equal v5. And so these vectors are linearly dependent because we can write one of them as a linear combination of the others. And one thing I'll actually point out here is that we know that each row can have at most one pivot, and each column can have at most one pivot. And so if we are looking to determine whether vectors are linearly independent based on the number of pivots we see, and specifically comparing that to the number of columns, then if we have vectors in R4 and we have more than 4 of them, then we are guaranteed to have a column that does not contain a pivot, and therefore we are guaranteed to have a linearly dependent set. So we're going to see that kind of formalized in a minute here. So let's take a look at proposition 246. This says that the columns of a matrix are linearly independent if and only if every column contains a pivot position. And that's what I was alluding to with those examples. And one of the ways to hopefully convince yourself that this makes sense is look at these different examples and notice kind of why a matrix not having a pivot in a column. So you can look at, all these different examples. So like this first one here, we had a matrix, we had, no pivot in column 2. And so, we could, I didn't draw the vertical line here, but if we drew this vertical line, then we could see that, maybe even ignoring, right? So we could ignore this third column. It doesn't really make a difference for this question. We can see that V2 is twice V1 from that reducer echelon form, and that second column did not have a pivot. Here we had pivots in each column, and so if we tried to play that same game, like drawing these vertical lines, we would end up always with an inconsistent system, right? So this third row would say 0 equals 1, so that doesn't work. And even if we tried to draw a vertical line here, again, we'd have sort of these 0 equals 1 rows, so that doesn't work. Okay, same thing with this example. No matter kind of where we put those vertical lines, we wouldn't be able to get a consistent system. Here we showed putting a vertical line in when we did not have a pivot. Sort of putting that vertical line right before your pivot will allow you to set up the specific linear combination. So we saw that here as well as here. And then proposition 247, talking about how many independent vectors can we have. So a linearly independent set of vectors in Rn contains at most n vectors. So in R4, if we have 5 vectors like we did in that last example, they must be linearly dependent. So if we want to have a set of vectors in R2 that is linearly independent, we can have at most 2. Once you have 3 vectors in R2, they're guaranteed to be linearly dependent. If we go to R3, once we have 4 vectors in R3, they are guaranteed to be linearly dependent. This is not an if and only if, so it's certainly possible that 2 vectors in R2 are linearly dependent, or 3 vectors in R3, or 2 vectors in R3 are linearly dependent. But once you have more than the dimension of your space in vectors, then you are guaranteed for them to be linearly dependent.